everything is working. And so let's restart from where we left yesterday. Okay, so we were discussing how to describe the vibrations of a hanging bar. I was discussing at the very end the boundary conditions, and let me rapidly start from there. A second. Okay. So let me restart from this boundary conditions. So what we did was to derive this partial differential equation, this one, and at variance with the prima si vedeva, vero? Forse quando ho girato l'aggeggio non si vedeva niente. Scusate un attimo che al solito c'è un problema, scusate un secondo. Non si è mai visto niente. Allora devo fare come ieri, devo provare a farlo ripartire forse. Ok, io devo ripartire perché sembra che normalmente anche oggi non si veda lo schermo. Avete pazienza un secondo, ragazzi, scusate. Allora, qua, restart. So sorry, I hope that now everything probably is working. And just, I have still to share the screen. I think present now your entire screen. Yeah, I mean, it's a little bit tricky, all this procedure, but anyway. And finally, to record. Ah, it's still recording. Okay, stop recording. Fine. Okay, so this is where we were yesterday, and so we derived essentially this partial differential equation that describes the vibrations of an elastic bar, longitudinal vibrations. So the setup was this one. We were thinking that we were attaching the bar, let's say, to the ceiling, and we were considering only longitudinal movements. We were completely neglecting what was eventually happening in the transverse direction. And we were using the law of elastic forces, and in that way we arrived to this equation. So what we were discussing were the boundary conditions, and we discussed the Dirichlet boundary conditions, which have an obvious interpretation, meaning that the two extremes of a bar are not moving for all times. And the normal boundary conditions instead have to do with forces, so to say. So this is where more or less I arrived yesterday. And the idea is very simple. The idea is we used this here, this law of elastic forces, assuming that there is a direct relation, a linear relation between the u over the x, which is how much I am stressing the material, the bar, per unit length, and the force, this tension T, which is acting on each element inside the bar. And K is the constant of proportionality. Could be even a constant if a bar is uniform. Okay. So this means essentially that if I give a specific value of this derivative at one or both of the extremes of the bar, I am essentially telling which is the value of the tension there. So if there is on one of the extremes no external force, then I can imagine to reach an equilibrium, for instance, if I impose conditions like this, because there is no external force, there is no tension, fine. But if there is some external force, and if I want to describe a situation in which some sort of equilibrium is reached, then I have to write some Neumann boundary conditions, but I cannot write zero. I have to write what? Let me do it now. Okay. So suppose that there is some external force, as I said. So if I want to reach some equilibrium, it means that the external force, for instance, let's say pulling on one extreme of elastic bar, must be exactly compensated by the elastic force. So the elastic force, for instance, I can write as minus A. A is the area of the transverse section. And after I have that constant, elastic constant, and for instance, I am evaluating all this at one extreme of the bar, and then I have the u over the x also evaluated at L. So this is the tension that is due to the elastic forces, so internal forces acting on the extreme of the bar. If I want to reach an equilibrium, it means that if I add some external force F, this has to be equal to 0. Okay. So in conclusion, if I am in a situation in which there is some external force acting at the extreme of the bar, then a useful boundary condition can be exactly the one that I get from here. The u over the x evaluated at that extreme will be equal to what I get from here, will be equal to F divided by A, K of L. Okay. So, as we have seen here, it means also that in general, these boundary conditions can be not homogeneous. The expression of homogeneous in this type of problems can take two completely different meanings. I can, for instance, say that the bar is homogeneous, meaning that, for instance, the elastic constant or the density of the bar is the same along all the bar. But there is a more technical interpretation of the more technical meaning of the expression homogeneous. And homogeneous for an equation means, for instance, in this case here, that there is not this term f, and in such a way I have u, the quantity that I want to determine everywhere. So an homogeneous equation in general admits the solution 0. U equals 0 is a solution if f is equal to 0. And similarly for the boundary conditions, if I put 0 for the Dirichlet or the Neumann boundary conditions, then I can say that these are homogeneous boundary conditions. So it's quite completely different meaning in the two cases. Okay, so what we have discussed here was the situation of this hanging bar, which is oscillating up and down, okay? But essentially the same equation that we have derived can be obtained also in a quite completely different setup that corresponds to vibration of an elastic string. So let's see this different setup. So this time, so this is another, I mean, we will get to the same, we will get the same equation, but in a significantly different setup. So the new setup is the following. Suppose that you have a string which is attached, let's say, on both sides. So this is 0, this is L. And you have your string, which is attached here and attached here. And as before, we are assuming that it is an elastic string, and therefore that Hooke law relating the displacement and the tension, the linear relation of the Hooke law is still valid. But in order to arrive to write the equation for the vibrations of this string, that will be essentially this one, we need to make some further assumption. So let me zoom on one element of this string. So let me, and suppose that I am deforming an element of this string in this way. Maybe I could make it slightly, sorry, just slightly less bent. Oops, something like this, let's say. Okay. And let me tell that this is an angle theta. So what I am saying is that I have essentially pulled the string that instead of being perfectly straight, now has made this sort of dent here. Okay, of course, after I will have something similar, maybe on the other side, but I concentrate on what happens essentially just in a little element of the string. That, as usual, if this is the x-axis, this will be between x and x plus delta x. Okay. So the length, the longitudinal length here is delta x, and I have an angle theta. So to derive that equation, we will make the assumption that theta is small, meaning essentially that I can decompose the way in which the position of this element of the string, which is this one, into two components. Essentially, I have, in principle, I have both changed the position. Let's say, let's call it, I don't know, U, this one, okay? So there will be a component orthogonal to x-axis, this one. But in principle, I have also changed something along the longitudinal axis. If I touch at this point here, in principle. So what I am instead assuming is that this angle theta is very small. So what I am assuming is the following. So the law of Hooke has to do with the total displacement, okay? But I can decompose the total displacement as a contribution along the x-axis and a contribution along the u-axis. So I can write something, let's say, as, let's introduce, let's say, a vector n. This vector n is essentially, let's say, this vector here. It's a vector, not a verso, it's a vector. And therefore, I have two components of this vector. I have, and let's call T the total length of n. So T is n1 squared plus n2 squared. Okay. So the two components, n1 is, let's say, nx, okay, and the other is nu. Okay. So these two components can be written as something like this, okay. Let's say n1. Oh, it depends really on the sign. I don't understand why it's using that sign. Ah, okay, because it is already thinking to the force. Okay. Okay, so the displacement, sorry, don't call this T. I don't think it's a very nice, sorry, don't call this T. It's not a very nice notation, I think. Let's call this just big N, okay? Because instead it's confusing, I think. Let's call this big N, okay? This is the modulus of this displacement. So the modulus of this displacement, of course, is this quantity here, and the two components, let's say N1, are equal to N. So N1 is the longitudinal component, is N cosinus of theta, and N2 is N sinus of theta. Okay. So if you prefer, you can write that tangent of theta is equal to N2 over N1, or in the other rotation, if you prefer, is N U, this vertical displacement, divided by Nx, the longitudinal displacement. Okay. So these are the displacement, and as I said, we assume again the law of elasticity, the Hooke law. So this means that since this Hooke law is essentially telling us that the force is proportional to the displacement, we can, of course, also decompose the force in a similar way. That is how the book does. Essentially, starts directly by decomposing the force instead of the displacement. But okay, doesn't matter. So what can we do? So we have essentially that our tension T at a certain point x can be decomposed, and we will have these two terms. So the tension, let me write it here, the tension is proportional to the displacement with a minus sign, okay? So it means, let me introduce a minus sign. Let me just do something like this. This is minus, the notation is really ugly, sorry. The notation here is really ugly. I don't know why I never noticed that this notation is really, really ugly. Okay. This notation is quite ugly, but anyway. Okay, so the idea essentially is that the angle theta is very small. So if the angle theta is very small, we can approximate cosinus of theta roughly with 1. And sinus of theta will be also similar to tangent of theta. And tangent of theta is what we just wrote right now as, let's say, n longitudinal divided, sorry, n transverse divided by n longitudinal. Okay. So in conclusion, when we write these two components of the tension can be decomposed, as I said, in a component which is longitudinal, a component which is transverse. And the longitudinal component contains also cosinus of theta as the displacement, but we approximate the cosinus of theta with a 1. So let's follow this notation, but I will have to rewrite this because it's really not properly written in my opinion. Let's write this vector describing the tension in the following way, with a minus t. This minus t just indicates essentially it should have been something proportional to n cosinus of theta. Okay, so it should have been something containing cosinus of theta, but this we put 1. And the second point is that this proportionality involves a minus sign, and so we'll write directly as minus t. Okay, as I said, it's not, I don't like very much the way in which this is written, but okay. So this is minus t, of course, evaluated at x. And the other component is similar. So there is again a minus sign because of the fact that the tension goes in the opposite direction respect to the displacement. And instead of writing the sinus of theta, I approximate with the tangent of theta, which is this object here. And so this object here, let's go back a moment here. This quantity is delta x, and this quantity here is delta u. So this quantity here is also some, let's say, delta u over delta x. And if I take delta u and delta x as small quantities, this is essentially du over the x. So here I write directly du over the x. Okay, let me summarize because this is not clean the way in which it's written. I must rewrite this. Sorry. So the idea is we we touch the string, and this angle, we assume that is very small. So what happens? That we can approximate this angle in this way. And the second point, we can ask ourselves what is happening here and here. So we are evaluating the tension here and the tension here. And in both cases, we are expanding, essentially, the tension in two components. So the two components are a longitudinal component of the tension containing a cosinus of theta and approximating cosinus of theta with a 1. And we write this minus t because it already incorporates the idea that the tension goes in the opposite direction respect to the displacement. And the transverse component, instead, that was containing a sinus of theta, but sinus of theta is similar to tangent of theta, and tangent of theta in turns is essentially the ratio between these two displacements. So if this displacement is delta x, the corresponding transverse displacement is delta u, and if they are both small, I can claim that instead of writing delta u over delta x, I write the u over the x. That is what I've done here. Okay. So all this essentially is just to try to understand how to decompose the total tension in two components, a longitudinal and a transverse, and how to relate in particular this transverse component to the transverse displacement. Okay, so this essentially is this initial part. So this I can do with the composition at each point inside the inside my string. At each point inside my string, I ask myself, how can I decompose the tension that works here? And I decompose as I did. And after there will be the tension, which is acting at x plus delta x. This is exactly the same, if you recall, to what we were doing in this case. We were considering the tension acting on this layer and the tension acting on the other layer. Okay. So we do exactly the same because essentially what we want to evaluate is the total tension acting on this little element in this case, and similarly the total tension acting on this little element in this other case. There will be a tension acting here and a tension acting there. Okay. So what I have to do is to put together these two components. So essentially I have the tension acting, let's say, at x plus delta x, and in principle at a certain time t, minus the tension acting at x and t. And I approximate, as I did now, both terms in the way in which I have just done. Okay. So this means, in practical terms, that I have a longitudinal component of the tension and a transverse component of the tension. Okay. So, as we have noticed here, the longitudinal component of the tension just contains, so to say, the modulus of the tension because the angle is assumed to be small. So what we can do in particular is to say that if we take of this tension the longitudinal component, this object here will correspond to some minus t of x plus delta x t, and the other to some t of x and t. And the point is that we are completely neglecting the longitudinal motion. We are assuming that the motion takes place only in the transverse direction. So if this is true, in order that it is true that the motion takes place only in the transverse direction, then these two forces, which are longitudinal forces, must cancel one with the other. So essentially what we have obtained is that a necessary condition in order not to have any longitudinal displacement is that the longitudinal component of the tension is the same in each of the points, so that there is no net deformation, longitudinal deformation. Okay. So now we can go to the transverse component. And for the transverse component, we have a similar decomposition. So, okay, I can write T x plus delta x t du over dx evaluated at x plus delta x and t. Oh, okay, sorry. Now I understand. Sorry. Now I understand. This minus sign that was written here, this minus sign refers already to the fact that exactly as it was in this case, exactly as it was in this case here, it already incorporates the idea that on one extreme, the tension points in the opposite direction respect to this, respect to x, and on the other extreme, the tension is parallel. So the minus sign was already incorporated, sorry, that minus sign was actually referring to the fact that if I consider a certain finite element, I have one component on which the internal forces of the string are acting in one direction, and on the other side of that element, the internal forces are acting in the opposite direction. So that's why, sorry, that minus sign that the book was incorporating was not referring to the minus sign of the Hooke law, but directly to the idea that you have, so to say, a tension force acting here, and this is an element inside this larger string. So therefore, the rest of the string is somehow pulling up. And we will do the same down here. Okay. So these are the two vectors. So this is at x plus delta x, and this is t of x. Okay. Sorry, the minus sign was that one. It was not really referring to the Hooke law. It was directly incorporating the fact that these two tension forces are directed in opposite direction. Okay, so it was already written here, this minus sign. Okay. So, okay. So it means actually that when I compute the total tension, I should write a plus here and a minus here. Because this is the positive tension acting at x plus delta x, and this is the negative tension acting at x. Sorry for this mess. There was something that was not clear while I was trying to reconstruct. Okay. So, okay, let's go back now to the transverse component. So the transverse component can be written like this, minus t of x and t, and we will have the u over the x evaluated at x and t. Yeah.
U versus is down.
Yeah, the U versus is down, but this is really completely arbitrary in the sense that it is some displacement respect to the equilibrium position, and there is really no preferred direction. I mean, what I have done here is almost nothing in the sense that we have chosen a certain direction of the axis U. Okay, and at that point, what we have done was just to assume that the tension is directed, the tension acting here is directed the same direction of the displacement. Okay, and this we did that at x plus delta x and also at x. Okay, but after it doesn't matter very much if it is up or down or whatever. The only assumption, so to say, that we have made is that the tension is directed along the same direction of the displacement. And after we have decomposed, and therefore if this displacement has this transverse component delta U, then as we have done here, this delta U over the x has to do with the tangent of theta, and so on and so forth. Okay, so yeah. Okay, so sorry, I made a little mess here with this minus sign that was really puzzling me. The minus sign was just due to the fact that it was already incorporating the fact that the tension at this point is directed opposite respect to the tension at this point. Okay, because essentially these are the internal forces which are stretching this little element on one direction and the opposite direction, exactly as it was in this other case, in which this element was pulled in the direction of the remaining part of the bar, and similarly for this one. Okay, so this is that minus sign, and not to do with the force, but just on the way in which we built this equilibrium of the forces, essentially, in this object. Okay. Okay, so conclusion. So we have noticed that, first of all, that if we want to describe a situation in which there is no longitudinal displacement, it is necessary that the total force, total longitudinal force, must be zero. Instead, that element is clearly moving. And that means essentially that the tension must be constant in the longitudinal direction at each point of the string. Okay. And the second is this equation here, which instead describes what happens concerning the forces in the transverse direction. And of course, we can make use of the previous equation. And therefore, instead of writing t of x plus delta x, we can just write t of x and t. And so we can write that the total force acting in the transverse direction can be written as t. I should write t of x, but we have just stated that it has not to depend on x. So let's write this very, very clearly. T of x is actually just t, does not depend on the position. So I have just t, and after what I have here is t multiplying this the u over the x evaluated at x plus delta x minus the u over the x evaluated at x and t. Okay. And as usual, I can rewrite this through an integral. So I can write this as t, and this will be an integral between x and x plus delta x, and I can write this as the second derivative of u of s and t respect to s square integrated ds. Okay. So this that I have written here is the total force acting in the transverse direction onto that element. Okay. There is no total force, no net force acting in the longitudinal direction, because if there was, the element would start moving longitudinally, what instead we are assuming that is not the case. And this describes completely the force in the transverse direction. Okay. So at that point, as we did in the previous case, we use Newton's law, and therefore we claim that this total force is equal to mass times acceleration. So we just claim that this object here must be equal to the integral between x and x plus delta x of the density of the object, and we have the acceleration, that means second derivative of u of s and t respect to t squared integrated ds. And this relation, of course, must be true for whatever x and delta x, and therefore we again arrive to the same equation that we wrote last time. Rho, second derivative of u of x and t respect to t squared minus or equal to second derivative of u of x and t respect to x squared. Okay. So this is the same equation that we obtained last time, and as you recall, this is what happens if you don't have any external force. Okay. If you have an external force, you have to modify this equation by incorporating explicitly, so the total force will not be just this term here, will be this term plus the external force. And so if there is an external force, you can, for instance, rewrite all this in the following way. You can rewrite as let's say, just a second, not to make a mess also here. So, okay, let's first rewrite this in a slightly different way without external force. Let me rewrite this as second derivative of u respect to time, and t over rho, let me call this velocity square. So minus velocity square du over dx squared equal to 0. So what I have written here is that the velocity square is equal to t over rho, the velocity square. And if you check, this does make sense. First of all, we can notice if you write the equation in this way, this c square must be a velocity square, meaning that the dimension of c is a velocity, so it is a length over a time. Okay, and therefore, if you check, this works in order that the equation is written correctly from the point of view of the how is called the quantities that enter the equation. Okay. And if you concentrate on this other relation, rho is a density. Rho is a density in this unidimensional problem. So rho is essentially, because you see, how did we get a mass? We got a mass essentially by integrating on L, okay? So this means that the dimension of rho is a mass divided by L. And what is a T, this tension? The tension that we introduced somewhere is a force. The tension is a force per unit length. Let me check if it works. So we can check from here essentially. Let's take dimension of T is equal to the dimension of C square rho. So how it works? C square is length square divided by time squared, and rho is a mass divided by a length. Okay, so is this a force? Okay, so this is a mass, a length, and a time minus 2. Actually, it's really a force. It's not a force per unit length. So the dimension of T is really a mass times an acceleration. Okay. And okay, so concerning how to introduce an external force, we can choose, in a sense, how we define this external force. And for instance, I mean, the book is writing the following: is modifying this equation here, introducing here an external force. So telling that second derivative of u respect to time square minus c square derivative of u respect to x squared, and here is writing f of x and t. So now it's better to check essentially which is the dimension of this f. So the dimension of f, is what? The dimension of this external force f, we can check by comparing with this quantity here, okay? So, okay, so we have essentially, let's take the first. So u is a displacement. So it is a length square divided by t squared. While we know that the dimension of a force should be this quantity here, so what does this mean that we have written a force in this way? So if I take, let's say, a real force m, L, t minus 2, t minus 2. And I divide by a density. So I divide by m L minus 1. What I get is exactly L square t minus 2. So it means essentially that this F is not really a force, but is better a force divided by a density, because this rho here, this rho here that we used was a density defined as mass over length. Okay, so if we write our equation in this form, we have to keep in mind that F, the dimension of F, is not the dimension of a force, and we can check from here, but is better a force divided by a density. Okay. Or if you prefer, you could also interpret as a force divided by a mass, and after still you have a length. So, okay, I think probably the best is to say that is the force per unit of density. Okay, so conclusion. We arrive to write this equation here, which is clearly of the same type of the equation that we wrote last time, that is still written here. Okay, so essentially it is very similar to this, and from here we see even better, because if we divide by rho here was really the density, then what we get is the quantity that now we were calling F. This was a force, this F here was a force, but now it's divided by rho. Okay, so just keep in mind that when you do these little tricks that you have to always check if you are referring to a force, if you are referring to a force per unit length, or a force per unit of mass, etc., etc. But the type of equation is exactly the same. And of course, the same consideration that we did before concerning the boundary conditions apply also to this case. Okay. So to summarize what we have done, let me just go back here to this equation here. So we came to the conclusion that this type of equation can describe both, for instance, the vibration of a hanging bar or the transverse vibration of a string. Okay. And okay, we have discussed the boundary conditions. Of course, I think I was mentioning that last time. This is also second order in time. So it means that there will be two initial conditions that need to be imposed. So we will, for instance, tell that, let's say, that u of x and 0 is a certain given function, psi of x, let's say. But this would not be enough, because this is second order in time. So for instance, we have to give also the velocity. So for instance, something as the u over the t evaluated again at all points at the initial time, and this can be another function, I don't know, gamma of x. So the problem is completely defined when I have this partial differential equation by giving two boundary conditions and two initial conditions. Typically, the initial position that can be the displacement, for instance, and the initial velocity. Okay, at that point, the problem is completely defined. Okay. There are questions on this part, because I made a little mess before with the sign of the tension. Is there any question? From home? No questions?
No, thanks.
No questions.
Okay. Then, before leaving this part, sort of introduction to partial differential equations, let me discuss essentially one last equation, because it enters quite a lot of physical problems. That is called the equation of advection. So we discussed the equation of diffusion. And as you recall, I was telling that we wrote the equation of diffusion thinking at the diffusion of heat. So the quantity that we were going to determine in that case was the temperature, and we had the Fourier law concerning the direction in which heat is flowing, etc. But essentially exactly the same equation works if you have diffusion or whatever else. Okay, so one way of moving some chemical from one region to another is to let it diffuse inside some medium. But of course, there is another way, which has to do with the idea that instead, if I have some chemical which is distributed inside a certain fluid, well, the fluid itself can move. And therefore, if a fluid moves, it carries that chemical with itself. Okay. So in reality, as you can imagine, there are situations in which both mechanisms are at work. You can have a situation in which you have some chemical, whatever it is, which is distributed inside a fluid, and the fluid is moving, and at the same time, that chemical is diffusing inside the fluid. So that situation is called, it's a combination of advection and diffusion. So advection-diffusion equation. So what we have to do is to write down the equation for advection. So advection just means that you have something that is embedded in a fluid, and for the moment you are not considering diffusion, but the fluid is moving. So how do you describe that situation? Well, it's rather easy in the sense that, first of all, we can tell how much of that chemical there is at a certain time in a certain region. So we can, for instance, say that in a certain region that, as usual, we assume to work in one dimension, so will be between x and x plus delta x. And we work in one dimension, so the transverse directions can provide at most an area A of the transverse section. And we can say that inside this sort of cylinder, the total amount of that chemical is U of S and T integrated ds. So this is the total amount of chemical at a certain time t inside this sort of cylinder. So if I want to evaluate how this changes, I have to take the derivative respect to time. So the variation per unit time is the derivative of this quantity that, I can write, of course, as A, and as usual, I interchange the derivative and the integral, and so I write integral between x and x plus delta x of du of s and t respect to time integrated ds. So what we have here now is the rate of change, the change per unit time of the amount of chemical or whatever it is in the region between x and x plus delta x. Okay. So what can we do now? We can try to interpret this change. We can interpret this change as due to the fact that the fluid is moving. So let's assume that the fluid is moving with a certain velocity c. So c is the velocity of the fluid. So if I have a velocity and if I have a density, I can write a flux. The flux is the product of the density times the velocity. Okay. So if I write something as c times u of x and t, this quantity describes essentially the flux of this chemical, which is moving because the fluid is moving, the flux evaluated at x and at t. But as usual, what we are interested, so this is our cylinder, and we have these two layers. This is x plus delta x. And before, the previous formula was describing the change of the amount of this chemical between x and x plus delta x. This was the change per unit time, the rate of change. And now instead, what I am writing here is a flux. So I can evaluate the flux at x and the flux at x plus delta x. Since I have introduced some transverse direction, I have to multiply the flux by the area of this surface in the transverse direction. So I can write that assuming that c is a velocity along the x direction, okay, so this corresponds to an incoming flux, and here would be an outgoing flux. So it means essentially that the net flux is A, okay, I can factor it, and after I will have U evaluated again at x and t multiplied by c. This corresponds to the incoming flux at this position x minus the outgoing flux, which is U of x plus delta x and t c. So this is the net flux inside this region. How much of this chemical enters at x minus how much of the chemical goes out at x plus delta x. And this, as usual, can be written as an integral. I can write this as minus the integral between x and x plus delta x. And I have c, which is the velocity of the fluid, and a. And I write a derivative of u of s and t respect to s integrated ds. So this is the net flux, difference between how much chemical enters, how much chemical goes out. a flux, you recall, is there is a velocity, so it has to do with what happens per unit time, exactly as it was in this other formula. This was the total change of the amount of chemical per unit time. So I can just equate these two quantities. This is how much it changes per unit time, the total amount of chemical in this region, and it must be equal to the net flux that enters that region. Therefore, I can write in conclusion that so these two quantities has to be equal. Therefore, I can write that the integral between x and x plus delta x, okay, I can write an a in front of everything, that doesn't matter really. And what remains is essentially, from here I get a du over dt. So I have du of s and time over dt. So this must be equal to minus, etc. So if I bring on the left-hand side, I get a plus c du of s and t divided s, all this integrated the s must be 0. And therefore, as usual, since this must be true for all x and all delta x, I arrive to the equation du of s and t respect to time plus c, or let's call this maybe instead of s, let's call it x. Du of x and t plus du of x and t respect to x equal to 0. So this is the equation of advection. This is the equation of advection. Okay. In this equation, c is the velocity of a fluid, and u is the density of our chemical that is carried by the fluid that is moving. Oh, this is first order in space and first order in time. So it means essentially that I have to give one boundary condition and one initial condition. So the initial condition will correspond to telling, okay, how much chemical I had at the beginning. So for instance, I can write u of x and 0, and this is some given function u0 of x. And after I have to provide some boundary condition. The boundary condition corresponds to the fact that I have essentially to tell what happens at one of the, this was a cylinder, for instance, at one of the extreme of the cylinder, telling is there some fluid that is entering or what. So you can intuitively understand that this process is very simple. Imagine that you have a pipe, and in the pipe there is some fluid moving, water, and there is inside the water some chemical, different densities depending on the position, and you are sitting, and in front of you there is the water flowing. So what you can see is that in front of you the density of this chemical is moving with the water. But of course, in order to describe completely the process, you need to tell, okay, at a certain moment, what I have in front of my eyes, and also what happens, for instance, on one extreme of the pipe. Is there some chemical that is entering at that extreme, so that after I will start seeing in the middle of the pipe? Okay. So I need to provide some one initial condition because it's first order in space. And so, for instance, I can tell that u at x equal to 0 and time is something, is some function phi of t. This essentially tells me, okay, I have in front of me the pipe, and I can see at any moment what happens at one extreme. That extreme, there is some density of this chemical that starts appearing, and after it will, of course, move, etc. So in general, if c, if the velocity is a constant, this equation can be solved rather easily. If a velocity of a fluid is a constant. Sorry. And what do we get? What do we get? For simplicity, let's completely neglect, so to say, the fact that we have to include also a boundary condition. For instance, if you have a pipe of infinite length, then you can neglect, so to say, what happens at minus infinity. You just look what happens in front of you at a certain moment that you take as initial moment. So as you can imagine, you see essentially this profile of density which is carried by the fluid. And this is easy to check. So let's assume that the pipe is infinite, okay? So we don't have a problem of telling what happens at one extreme of the pipe. And let's assume that, as was written here, at a certain moment, there is this distribution of chemical, u0 of x at time t equal to 0. Then it's easy to check that the solution u of x and t can be written as u0 of x minus ct. So this is what happens if a velocity is constant, okay? And easy to check because you just substitute here. If you take the two derivatives, the derivative respect to time provides you a minus c times the derivative of u0 respect to the argument, and here you have plus c, the same quantity, so they just cancel, and therefore you satisfy this initial, satisfy this equation, okay? Because you get an extra c when you differentiate respect to time, you get a minus c, okay? That cancel against this other piece. And of course, at t equal to 0, this satisfies this condition here. So there are situations in which this equation is very simple. Of course, it's not true if, for instance, the velocity is not constant, etc. As I was mentioning, in the real world, very often, the process of advection, that means some chemical which is moving with a fluid, mixes together with the process of diffusion, providing this advection diffusion equation. So the equation of diffusion is the one that we discussed last time, I think. We discussed the diffusion of heat, but okay, as I said, it's the same equation, just change the interpretation of these quantities, and you get, let's see where it's going now. Look, somewhere I don't see. Maybe I wrote it here. Strange. Oh, it disappeared. Should remain. It's here, isn't it? Now it appeared. Here, okay. So this is our equation for the diffusion of heat, and we ended up by using the Fourier law that is connecting the temperature U with the flux Q. So it's essentially telling that the flux of heat goes in the opposite direction of the gradient of the temperature. And we ended up with this equation here, where U is the temperature. But as I was saying, the same equation applies if you are not thinking to diffuse heat, but to diffuse some chemical. So essentially what you get is something like this. Oops, sorry. So we had here the equation of advection. That is gone now at the very end. Sorry, here. The equation of advection is this one. And here, as you recall, we were equating the change of the amount of chemical which was regulated by this formula here. This is the change of the amount of chemical between x plus and x plus delta x. We were saying the only source of this change is the fact that the fluid is moving, carrying the chemical with it. And so we equated this change with the net flux inside this region. But of course, if instead there is some process of diffusion, then this can change also because of the process of diffusion. So if you put together the process of diffusion, as you recall, contained a second derivative in space. And so instead of getting this du over dt, this is a t, equal to minus c du over dx, this is what we got now, okay? On top of this, you have plus something which is proportional to the second derivative respect to space. So if you don't have this term here, if you don't have a term linear in the linear in the derivatives, the first order derivative in space, you end up with the equation of diffusion. The u over the t is equal to a constant times the second derivative with respect to space. Instead, you can combine because they both contribute to changing the amount of chemical in a certain region of space per unit time. Okay, so essentially, I just put together the two ingredients. The equation of advection that we derived, the u over the t was just equal to minus c the u over the x, and the equation of diffusion that was instead telling of the change, the u over the t, is proportional to the second derivative of u respect to x squared. Both they can contribute, and so you get this more general equation, which is the diffusion advection equation of similar names. Okay. Okay, so I would stop here concerning this part, and we can start another problem, which has to do with how we try to solve our partial differential equations. Unless you have questions on this part here. Okay, so what we are going to do today and for 1, 2 of the next lessons is essentially some Fourier decomposition. It's something that we have already seen in other courses, so I will go through very rapidly because most of it you have already seen. But I don't think I can skip completely because instead the risk is that you don't match perfectly what we are using with what you already knew. So I will tell again a certain number of things that I'm sure you have already seen, but okay. So let me add here something. Let me call this Fourier analysis or whatever. Just this is a Fourier analysis. Okay. Fourier. So the starting point of this analysis is, okay, first of all, we are concentrating on for the moment, on one specific type of equations. So let me just go back a second here. So you recall that essentially we have discussed the equation of diffusion and the equation of the waves. And let me show once more. The equation, here it is. The equation of diffusion is this one. And we discussed also the situation in which we are looking for time-independent solutions. So that situation corresponds to the case in which the u over the t is 0. And of course, f must be time-independent. And we start by discussing, and as you recall, we get an equation, the equation minus derivative with respect to s equal to f of x, which is the same as the equation that we get, here, describing instead vibrations, time-independent vibrations, of course, with a completely different interpretation of the various quantities. So why we start by discussing what happens just concentrating on this part of the equation. So, okay, as I said, this corresponds to time-independent problems, but there is another and more interesting reason, and the reason is that if we solve the time-independent problem, so as we will see, if we are able to write, for instance, our solution as a Fourier series, then we can try to solve the entire problem, so the time-dependent problem, by expanding the solution on that Fourier series with time-dependent coefficients. So the strategy that we are going to follow is, first of all, we discuss the time-independent, the static problem. We start by using the Fourier decomposition. After we will, in our course, essentially, we study three techniques. The first technique is this Fourier decomposition that you have already seen, because it's the same Fourier decomposition that you have used in quantum mechanics, for instance, where you have the eigenvalues and eigenfunctions of the Schrödinger equation, and you write a basis, you expand whatever on that basis, so on and so forth. We are exactly doing the same. That's why I was telling part of this you have already seen, but I will repeat because instead maybe you miss some little link. And after we study instead two other techniques. So this technique, in a sense, can be done sometimes, if the equation is simple, with just paper and pencil. You are able sometimes to obtain the eigenfunctions of your problem and if you are able to get the eigenfunctions and the eigenvalues, then in principle you can solve a problem almost without using the computer. Okay. But there are the two techniques that we will see instead in the following, in which essentially we are not really expanding on the basis of the eigenfunctions of the time-independent problem. Instead, we will introduce some sort of simplified basis, and we will expand on this simplified basis. The idea is not completely different. The idea is that, again, we split the problem into finding a certain basis. This basis not necessarily is the basis of the eigenfunctions of the time-independent problem. And after, we solve the total problem by introducing coefficients in this function which are time-dependent. So there is some similarity. Okay. The third technique instead is quite significantly different, because the third technique, so the second technique is called technique of finite elements. It's called technique of finite elements because we will introduce a simple base made of a finite number of elements. In the case of Fourier, in principle, you have operators in which you have very often an infinite number of terms in the basis. And there we will simplify taking finite base. That is not, of course, a base, but is a truncation. And the other and third technique that we are discussing is called instead finite differences. And it's completely different. It corresponds to starting from one of these equations and everywhere rewriting the derivatives in terms of finite differences. So instead of writing, I don't know, the u over the x, you substitute with u evaluated at x plus delta x minus u of x divided by delta x. And in that way, you transform your problem into a very simple sort of algebraic problem, and you solve it. Okay, so this is what we have in front of us. And so the first step in this procedure is this Fourier decomposition. So as I said, this is essentially the same that you have seen when you have studied, for instance, quantum mechanics. We will go through this relatively rapidly, just so to be sure that there are no hidden aspects. So we start, as I said, by considering the time-independent problem. And to be very concrete, let's start from this problem here. Minus a constant, second derivative of u respect to x squared equal to f of x, with two boundary conditions, u of 0 equal to 0 and u of L also equal to 0. So suppose that we have this problem here. So is time independent, and we have imposed the two homogeneous Dirichlet boundary conditions. So what we are claiming is that there is a strong similarity between this problem that involves, of course, a differential operator and a problem of linear algebra. So notice here, the quantity that we need to determine is this quantity u. And instead, let's consider, for instance, the problem ax equal to b, where, of course, A is a matrix and x is a vector, okay? And what I'm claiming is that there is a strong similarity between these two problems. Oh, similarities. The subtle point, so to say, to be understood, is essentially the following: under which conditions these two problems provide one and only one solution. There is one and unique solution. And the problem essentially, I mean, the existence or non-existence of a unique solution, or better, situations in which the solution is not unique, can be framed in a similar way in the two cases. In the first case, the case of our not homogeneous differential equation, you recall that the problem is that if we have the corresponding homogeneous equation in which we put f equal to 0, okay, we can solve it, and in this specific case, we know that the solution of the homogeneous equation are whatever linear function. So if I concentrate on the problem, let's say minus t second derivative of how to call this, phi respect to x square equal to 0, I know that the solutions are of the form phi equal to ax of alpha x plus beta. So this means that if I don't include the two boundary conditions, u of 0 equal to 0, u of L equal to 0, of course, they could be also not homogeneous, but suppose, for instance, that I have these two boundary conditions. So if I don't include boundary conditions, then the original problem is not a unique solution. Because if I go back to the original problem and I claim that I found a certain solution, whatever, u bar, then to that u bar solution, I can always add phi and still a solution, because phi is just annihilated by the differential operator. Okay. So in order to get a problem that admits one and only one solution, in this case, I have to add these two equations, okay, which are boundary conditions. So let's go to the other problem, the problem of linear algebra. So in the case of problem of linear algebra, the analogy can be the following. Suppose that I have a problem where x belongs to, let's say, Rn, so contains n components. So let's say I have x1, x2, xn, which are my unknown. Okay. But suppose that the matrix A instead belongs to some, so the first index here is the number of row. So let's suppose that is n minus 2 n. And of course, this means that B is Rn minus 2. So in this situation, I have n unknowns, and I have imposed only n minus 2 conditions. So it is clear that in this situation, the solution is not unique. And if I want to get one and only one solution, I have to add other conditions to the problem. Okay. So from this point of view, I can imagine that my original problem, which was a differential equation problem, this differential operator, can transform into this linear algebra problem, And the idea of having a problem which is completely determined, meaning that I have to include these boundary conditions, means that the original matrix was too small. The problem was not completely determined because I did not impose enough boundary conditions. Okay. So, okay. So let's try to be a little bit more explicit in this analogy. So what essentially we want to do is to use some language of linear algebra into our problem of differential equation. This is something that you have already done, as I said, when studying, for instance, quantum mechanics. In the case of quantum mechanics, as you recall, a special role is played by the Hermitian operators. Point is, in quantum mechanics, you have typically the wave function, which is a complex object, and so you are dealing with matrices, eigenfunctions that are complex numbers. But here, in our equation of diffusion or equation of vibrations, we don't have really complex numbers, we have real numbers. So the analogy, of course, of having Hermitian matrices is to have symmetric matrices. And so first of all, we want to see what it means. A symmetric matrix is obvious. Let me be slightly more explicit by telling what it means to have a symmetric differential operator. That is what really matters in our little analysis. Okay. So let me introduce a symmetric differential operator, symmetric linear differential operator, telling that this differential operator is symmetric if it satisfies the following equation. Okay, I write it, I comment. Let's call this operator K. KUV equal to UKV. And this is for all U and V. Okay, so what do I mean here with this notation? First of all, I have introduced a scalar product. So I mean, if I have something as F and G, this means the scalar product, means the integral, let's say, on the x of f of x, g of x. Okay. Extended from all the space, from A to B. Okay. And U and V are whatever functions that belong to the space on which my differential operator is acting. Okay. So if this happens, I am claiming that my differential operator is symmetric. Okay. Let's provide immediately an example by noticing that when I make the claim that a certain differential operator is, for instance, symmetric, is not enough to tell that, for instance, my differential operator is the operator second derivative. I have also to specify the boundary conditions. And only that way I can make the claim that my differential operator is symmetric. So let's go back to our original problem here. So the differential operator is essentially the second order derivative, okay? But if I want to ask myself if this differential operator is or is not symmetric, I have to consider these boundary conditions. So what I am claiming is, okay, is the differential operator second derivative, but I restrict its action on a specific subspace, the subspace of the functions which are satisfying these boundary conditions. So for instance, they are vanishing at 0 and at L. So instead of claiming that my differential operator acts onto C square 0L, so this would mean the differential operator acts on the space of functions which are continuous and differentiable continuously up to the second order, okay, in this interval 0L, but it will not be sufficient. I have to restrict, let's introduce this D. So this D means essentially that these objects belong to the class of functions which are continuous up to the second derivative in the interval 0L, and these objects are satisfying phi of 0 equal to 0, phi of L equal to 0. Okay, so I am now restricting. So my claim about the fact that a certain differential operator is symmetric is a claim that I make if I restrict myself to this specific subspace. Okay, so it is easy to see how this is crucial. Let me check it. So I want to check, for instance, that this operator here, that call LD, is the operator minus t second derivative of u over the x square. Okay, I want to check that this differential operator, when acting onto that space that I have defined, that is the space of functions having a continuous second derivative and vanishing at the two extremes, then this operator is symmetric. Okay, it is very easy to do. I'm pretty sure you have done something similar. And so I want to check explicitly that this, where is gone, this equation here is satisfied. Okay. So what I'm claiming, as I said, is that LD, when acting on this C square, C2, restricted between A and B, is a symmetric operator. So let's take whatever function belonging to this space. Let's write the scalar product LDU, where U is one of these functions. U and V belongs to this, okay? U and V belongs to this subspace. So I want to check that LDU scalar product V is equal to U scalar product LDV. Okay, this is very simple because the definition of this object is T is just a constant. It could have dropped it. Okay, doesn't matter. It's minus T, and this is the integral between A and B of the second derivative, so is U second V, dx. And what I do now is, of course, to make a first partial integration. And the first partial integration gives minus T U prime V between A and B plus T, the integral between A and B of U prime V prime dx. Okay. So this is the first moment in which we use the fact that the functions u and v are restricted to that specific subspace. Because of that, here we are evaluating v at b and at a. So this first term here can be put to 0 because v satisfies the boundary conditions. So I integrate once more, and if I integrate once more, I get t u v prime evaluated between a and b minus t, the integral between a and b of u v second dx. And this time I am using the fact that also u belongs to that subspace, and therefore u of b is 0, u of a is 0. So this first term can be neglected. And this object here is, of course, nothing else than what we started, but with the operator acting on the other side. This can be written as u, the operator LD. Apply on V. So what we have shown is that indeed our differential operator acting on this restricted subspace, so, is a symmetric operator. Okay, it's a symmetric operator. Oh, there are a certain number of little theorems that you have already seen. As I said, I will very rapidly just browse through them. So essentially, what we can do next is to study the eigenvalues and the eigenfunctions of this symmetric differential operator. Okay, so suppose that we have in general a symmetric differential operator, and we want to study eigenvalues and eigenfunctions, meaning that we want to solve a problem ku equal to lambda u. Okay, so what we can show is that the lambda are real. And it's easy to do that because we use the fact that k is a symmetric operator. So remind you that symmetric operator means that k u v is equal to u k v. So this means in conclusion that k u u is also equal to u k u. Okay, fine. So what happens if in principle lambda, so we want to check that lambda, as I said, is real, okay? But in general, suppose that lambda was not real. If lambda was not real, then what we would get is that we generalize our scalar product f and g in the following way. We write as an integral between a and b of f of x g complex conjugated of x dx. Let's assume that in principle we can generalize the scalar product to situation in which we have complex numbers in this way. So the operator is symmetric, so it satisfies this equation here. But of course, what happens? From this first writing, KUU, we recall that KU is lambda u. So this object here means lambda integral in the x of u squared. Okay. While the second object, the lambda is here. So suppose that, assume that is not real. Okay. Then what we would get would be lambda bar integral the x of u squared. But then this implies that lambda is equal to lambda bar, meaning that lambda is real. Okay. So if you have a symmetric operator, so the fact that the operator was symmetric has been used essentially by writing KUU is equal to UKU. And at that point, what happens is that you can obtain this structure here. And therefore, lambda must be equal to lambda bar. That is absolutely the same that you have already seen when you were dealing with Hermitian operators and you were checking. Another thing that is easy to check is that if you have eigenvalues which are different, the corresponding eigenfunctions are orthogonal. So suppose that you have two distinct eigenvalues of two objects, u1 and u2. So suppose that you have k u1 is equal to lambda 1 u1 and k u2 is equal to lambda 2 u2. Okay. Then what you can do? Let me write lambda 1 u1 u2. And we have already checked that lambda 1 and lambda 2 are real, so I don't have to be worried about putting complex conjugated anywhere. So I can put inside this scalar product the lambda 1, so I can write it as lambda 1 u1 u2. But lambda 1 u1 is k u1, so I can write as k u1 u2. And now this is the moment in which I am using the fact that the operator is symmetric. So if the operator is symmetric, this can be written as u1 k u2. But k u2 is lambda 2 u2, so you get u1 lambda 2 u2. And therefore, I can pull out the lambda 2 again. They get lambda 2 u1 u2. So in conclusion, I can write lambda 1 minus lambda 2 u1 u2 equal to 0. And this means that if lambda 1 is different from lambda 2, the scalar product of the two eigenfunctions is 0, so they are orthogonal. Okay. There is an important property that pertains to this specific differential operator that, as you recall, is essentially also the operator kinetic energy, because is minus a positive constant second derivative. So, and the little property that is easy to check is that its eigenvalues are all strictly positive. So let's try to check that. So we can write, for instance, the eigenvalue lambda can be written as, okay, I assume that I have already normalized as usual UU equal to 1. Okay, I can always normalize my eigenfunctions. So I assume that I have normalized to 1 the eigenfunction. So lambda can be written as lambda UU. And this can be written, of course, as lambda U, or since by hypothesis lambda is an eigenvalue of U, as this differential operator LDU. Okay. So now let me write explicitly this differential operator. And this was minus t. And I have the integral because of the scalar product, integral between A and B. And there is the second derivative of U respect to x squared U, the x. Okay. And now I can take one integration by part. And therefore I get minus t U prime U, all this evaluated between A and B, plus t, and I get the integral between A and B. And so I have now to differentiate the U. And so I get U prime squared dx. So this first term is 0 because U at A and U at B is 0 because of the boundary conditions. And so the conclusion is that lambda is equal to t, that by hypothesis is a positive constant, times this integral. It is obvious that this integral is always positive or at worst equal to 0. But actually, the case in which it is 0, it is easy to check that corresponds to the trivial solution U equal to 0. Why? Because suppose that this integral is 0. So this integral is 0 only if U prime is equal to 0 everywhere. Okay? But since we know that U of A is equal to U of B is equal to 0, since the derivative now we have seen has to be equal to 0 everywhere, this implies that U of X is equal to 0 everywhere. Therefore, the only situation in which this quantity is equal to 0 is the situation in which we have a trivial solution. In all other cases, lambda is strictly positive. So this is quite a useful property because we can directly assume that the eigenvalues of this operator are positive numbers, and we will classify the eigenvalues in that way. Okay, we still have some 10 minutes, and let me just maybe provide a trivial example of what we want to do. So let me tell again which is the strategy that we want to follow. So we have seen that there is an analogy between certain linear problems and the differential operators, as you had already seen in quantum mechanics. And the main difference with respect to quantum mechanics is that when we study the equation of diffusion or the equation of the waves, we are not dealing with complex numbers. So instead of having to study Hermitian matrices, we restrict to symmetric matrices.
Why symmetric matrices? Because they have a lot of interesting properties. We can, in particular, expand on a basis, and we can generate the basis because we know that, for instance, the eigenfunctions corresponding to different eigenvalues, they are orthogonal. So we just build our eigenvalues in correspondence to each eigenvalues there will be an eigenfunction, what are sometimes called pairs, these things, eigenpairs are called. And at that point we will have a basis, and we expand everything of our equation on that basis. Where everything means what? Means that if I have in front of me an equation as the one we started from, where it's going here. In this equation, we have, for instance, f of x, okay, and the solution, which is u. So the strategy is, okay, we have a specific differential operator with specific boundary conditions. We have noticed that the existence of the boundary conditions is crucial because instead the solution is not unique, something that we can interpret also in terms of linear algebra, as I mentioned. After we have included our boundary conditions, and we can ask ourselves if the operator that we are studying is symmetric. If it is symmetric, we are happy because we can apply all this technology that we have already rapidly checked. So it means, in conclusion, that we select the eigenvalues and eigenfunctions corresponding to the differential operator, satisfying therefore those boundary conditions, and we will expand both the solution u and the function f on that basis. Okay. Let me provide a first little example of what I mean. We can do this very rapidly because we have already seen this example for sure, because it's nothing but what happens if you have the kinetic energy operator with these two Dirichlet conditions that the solution has to vanish at A and B. If you think a moment, for instance, let's take 0 and L, this corresponds to an infinite potential well in quantum mechanics. Okay, so you recall that you have the eigenfunctions, which are essentially sinus functions, and the eigenvalues, etc. So let me just very rapidly write that. So let's concentrate again on that differential operator. So it's still minus t second derivative respect to x squared, with these boundary conditions, u of 0 equal to 0 and u of L equal to 0. So we know which are the eigenfunctions and the eigenvalues, and you know that in principle the solution can be written in terms of sinus and cosinus, but after we fix the fact that it has to vanish at 0, it has that must be sinus and not cosinus, and after we get cosinus of blah blah has to vanish at L, and from there we get the discretization. So essentially, okay, sinus of L is equal to 0, so from there we get discretization. So essentially, we know that the eigenfunctions, let me just do it very rapidly, the eigenfunctions must be something of the form sinus of, let's say, theta x, but we also know that sinus of theta L must be equal to 0. Oops. Slow, strange. Okay, just in time. So sinus theta is equal to 0. So this means essentially that theta must be equal to n pi. Okay, and we can take n equal to 1, 2, etc., etc. N equal to 0 just gives the trivial solution 0 everywhere. And therefore, and after we can compute the corresponding eigen values, and the corresponding eigenvalues are, oh sorry, there is something that, sorry, theta, okay, sorry, yeah, okay, sorry, okay. Let's take this quantity here for a second equal to 1. Okay, instead is wrong. Okay, let's take this t equal to 1 for a second. Okay, fine. Now it's fine. And therefore, the corresponding eigenvalues are lambda equal to n square pi square over L square. With n equal 1, 2, etc. So we have these eigenpairs. For each eigenvalues, there is one eigenfunction that corresponds to, so theta is this object here. Theta L is this object here. Theta L is this object here. Therefore, okay, the corresponding eigenfunctions are sinus. Instead of theta, I have to write n pi over L. So sinus on n pi over L x. And these are our psi n of x. So these are our eigenpairs. I mean, I've not really done the calculation, but you have seen this many times, and I'm sure you don't need to do it. This can even be normalized. As you recall, the normalization, I mean, if you compute psi n, that means essentially the integral between 0 and L dx of this sinus square of n pi over Lx. As you recall, the average value of sinus square is 1/2. So this quantity here is just L over 2. So it means that if I use the psi n written in this form, after I have to divide by the normalization, which is this L/2. And okay, I wanted to provide an example, but maybe it's too rush. So I will, no, wait, okay, next time we provide a trivial example. The trivial example corresponds to, where is going now? Corresponds to solving, let's say, this equation, so the equation minus second derivative of u respect to x square equal to f of x with these conditions, of course, u0 equal to ul equal to 0. In which way? By expanding everything on this basis. So we will write that u will be, let's say, a sum on n of Cn sinus of n pi over Lx. And how to determine the coefficients Cn? Well, we have to expand also f of x on the same basis. So f of x will also be expanded as a Fourier series sum on n of coefficients an of sinus of n pi over Lx. And of course, we know how to compute the an because are nothing else but the projections of f of x on the basis that we have seen. Okay, so we will finish this better maybe next time. What I wanted to tell, just to conclude, is that in order to use, you will see this many times, but let me tell already. In order to use the Fourier technique, it is absolutely crucial that the base that we are using satisfies the boundary conditions. Because all this analysis started by saying, be careful that a certain differential operator by itself is not symmetric or whatever. It depends on the boundary conditions that you are imposing. You have seen this, for instance, in the case of the momentum operator, that you recall that is not Hermitian if you impose exactly this type of Dirichlet boundary conditions. And instead it becomes a Hermitian operator if you impose periodic boundary conditions. So the boundary conditions are crucial in order to tell if an operator is symmetric. And therefore, the basis has to be the basis determined not just by the differential operator, but by differential operator plus boundary conditions. The question is, what about f of x? Because f of x is a generic function that need not to satisfy the boundary conditions, because we choose it, okay? So is there really a problem in the fact that f of x will in general not satisfy the boundary conditions, or we are still happy? And we see that we are still happy in the sense that when we will expand f of x exactly in this way, we will notice that this expansion does not converge point by point. It converges only on average. It's something that next time I will spend little time on that. And that is enough. It's enough that it converges on average, and the solution instead will converge point by point. Okay. We provide a little example. We see that the way in which this will converge is not so satisfying in general, but the solution is fine. Why the solution is fine? We can intuitively understand. Suppose that f of 0 is not 0. F of 0 is a given number. Then it is obvious that this expansion will never be able to provide f of 0, because if I expand in this way, I always get 0. But do I have the same problem with u? No, because u has to satisfy the boundary conditions, which are exactly the same that I have already imposed in order to get the eigenfunctions. So the convergence of this series, the series of expansion of f of x, will not be point by point. There will never be convergence in x equal to 0 if f of 0 is different from 0. But that is not a problem, because it will still converge on average. If I integrate on all x, I am happy. And that is enough to guarantee that after there is a convergence for the solution, because the solution, after all, is satisfying exactly the same boundary conditions as the eigenfunctions. Okay, so we'll check again this, but okay, I little bit rushed through this part, but I know that you have already spent a long time in quantum mechanics, mathematical methods of physics, on Fourier analysis, so I thought that I could go fast. Do you have questions concerning this? Is it okay? Okay, then we will still spend at least one lesson in discussing the Fourier analysis, and after we will move to that other technique, which is the finite element technique. Okay, if you don't have questions, have a nice end of the week, and see you on Wednesday. Ciao.
See you, thank you.
Arrivederci.
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 Ciao, ciao, ciao. Ok. Allora, stop sharing. This is stop recording.